This is number 25 from 11.3. It's the sum from n equals 1 to infinity of 1 over n squared plus, that's a n cubed right there. And the directions are, I'm assuming, to determine whether or not it converges. So here we go. Let's try the integral test. You've got to check three things first. You got to make sure it's positive. So what's positive? Well, the related function f of x. Remember, the related function is 1 over x squared plus x cubed. You've got to make sure that it's positive and continuous and decreasing in order to use the integral test. So is that going to be an issue?
No.
It's positive, right? For x bigger than 1, it's positive. So f, we'll say f is, well, I'll do it using symbols. F is greater than 0 for x bigger than or equal to 1, for sure. So positive, for sure. Continuous. So f of x equals 1 over x squared plus x cubed is a rational function, meaning it's the ratio of two polynomials. Rational functions are continuous. And so is continuous. And that's kind of, you're just checking it off the list. We know it's continuous from Calc 1. And then the third one is that it's decreasing. So how do we show it's decreasing? Do you remember?
Derivative.
Derivative, yay. F prime of x. You could use the quotient rule, or you could write it as x squared plus x to the third, the whole thing to the -3, and use the power rule and the chain rule. I'll just use the quotient rule. Low d high. Okay, the low function is x squared plus x cubed. Well, what's the derivative of the high function? What's the high function?
2x plus 3x squared.
Well,
sorry, 0.
0, yeah. So,
I was going ahead.
So you're working ahead of me. You're too fast for me. Low d high, so that whole thing is just 0, minus high, which is 1 d low. And so you told me that's 2x plus 3x squared?
Yeah.
And then all over what?
X squared plus x cubed all squared.
X squared plus x cubed all squared. Okay, and then if you simplify this, it just becomes negative 2x plus 3x squared over x squared plus x cubed, the whole thing squared. Is that going to be less than 0 for x bigger than or equal to 1?
It's going to be decreasing.
Well, the thing is, you need to show that the derivative is less than 0 to show that it's decreasing.
Okay.
But it is, right? Because this guy in parentheses is bigger than 0. Just in parentheses, that guy's bigger than 0 for x greater than or equal to 1. And then this guy is always bigger than 0 as long as x doesn't equal 0, and it's not. For x greater than 0, greater than 1, I should say over here. For x greater than or equal to 1, this guy is always positive. So if you take a negative of something that's always positive, you know it's going to be less than 0. There's no issue there. And you don't even need to think about it as much as I'm thinking about it right now. So this is true for x is greater than or equal to 1, but so the derivative is less than 0 for x is greater than or equal to 1, which means the original function is decreasing. So f is decreasing. And so the integral test applies. It applies. IT applies. So that's the first part of it.
On the test, do you want us to state right after doing the 1, 2, 3 steps that the test applies, or can we say once we finish that it either converges
Well, we
or
still have more.
diverges by the integral test?
Yeah, I wouldn't be picky about that, as long as you show 1, 2, 3 is true.
Okay.
Positive continuous decrease. And so now, since the integral test applies, we can take the related integral 1 to infinity of f of x, which is this guy, dx. And then if that guy converges, the original series converges. If that integral diverges, the original integral diverges. Excuse me. So do you recognize which method we're going to use to integrate this thing? I mean, first of all, let's go ahead and write it using the proper limit notation. The limit as b goes to infinity of the integral from 1 to b of 1 over x squared plus x cubed. Do you remember which method you would want to try to use on this thing to integrate it?
To integrate the integral, we take
Go ahead.
the limit out separately, and then we integrate the integral with b and 1, and then solve it through there.
Yeah, but I'm talking about just finding the antiderivative of that.
Oh, we split apart the function into what you mentioned earlier about like taking out the, say, x squared and then doing them as separate functions.
So we're going to take out x squared, and then what's left?
Integrating. And then x plus 1.
X plus 1. And then what do we call this process?
I don't know.
I'm going to split it up into 2 separate fractions. So remember, that's partial fractions.
Oh, partial fraction decomposition.
Partial fraction decomposition, yeah. So actually there's going to be 3 of them, because we can think of this guy as a repeated linear factor. And when that happens, we're going to have one denominator that's x to the first power, and then one denominator that's x squared, and then the x plus 1 is just a non-repeated linear, so we'll just have one term or one fraction added in with one of those in the denominator. This is called partial fraction decomposition. On top, we're going to have constants a, b, and c. Does that look familiar?
Mm-hmm.
Yeah, it's been a while, hasn't it? Okay, so if we want to integrate, if we want to find the partial fraction decomposition rather, let's go ahead and clear the fractions. What are we going to get? Let's see, a just times x plus 1. Do you buy that so far?
Mm-hmm.
Plus just b times x plus 1. Plus c times just x squared. Does that look okay to you?
Mm-hmm.
Okay. And then let's see if we can figure out a shortcut for finding a, b, and c. So what would be a good number to let x equal?
-1.
Sure, that works.
1.
That works for me. So -1. Okay, if x equals -1, this whole guy, gone, right? This guy, gone.
Mm-hmm.
And then this guy is just c, isn't it? Because it's -1 squared.
Mm-hmm.
So c equals 1. That works. What's another value?
0.
How about x equals 0? So if x equals 0, what do we get? Well, this guy is 0. This whole term is not 0. It's b, isn't it? And then this whole term is 0.
Mm-hmm.
So we get b equals 1 in this case?
Yeah.
And then we just need to figure out another number to plug in to get c. Or not c, a. Well, just make a number up that's not -1 or 0. That's not something we've already plugged in. How about x equals, let me do it down here, x equals 1. Now, if we do that as is and we don't substitute, then what do we get? We get 1 equals, okay, what, 2a? Plug a 1 in there, 1 in there. 2a, and then 2 plus 2b. We plug a 1 in there. And then plus c.
Mm-hmm.
But we know 2 of these. We know c equals 1 and b equals 1. So what is this? 1 equals 2a plus, what, 2 plus 1?
2 plus 1.
Do you buy all that?
And then subtract the 3.
So that's -2 equals 2a, or a equals -1?
Yeah.
Okay, so we've got them all. We've got the a, the b, and the c. So we'll decompose this guy, and then the time in will be over here because I didn't want to put all that down here. So
Oh, this question has it all.
I know. It's a long one. So this is the limit as b goes to infinity, integral 1 to b of, okay, what was a? -1, so -1 over x plus b over x squared. Well, that's 1 over x squared. Plus c, what was c? C was 1 over x plus 1, like that. There we go. Okay, now we're ready to integrate at least. So limit b goes to infinity. Do you remember what the first guy is, the integral of the first guy?
-1 over x.
But if you integrate it, you get negative, remember it's natural log of, you could say absolute value of x, but since x is positive, you could just use x.
Oh, on my homework, I'm doing it in a different order. I did the second one first.
Oh, okay. And so what did you get for the second one? Minus 1 over x, you said?
Yeah.
Sure, that works. And then what's the last one?
Natural log of x plus 1.
Natural log of x plus 1. Okay. And then we've got to, before we evaluate the limit, we have to evaluate this from 1 to b. So we get the limit as b goes to infinity. Okay, just plug in the upper limit first, negative natural log of b minus 1 over b plus the natural log of b plus 1. And then minus, what do we get when we plug in 1? Right there, that zeroes out, right? And then minus 1, and then plus natural log of 2, all in parentheses though. Let me pause for a second. Do you believe all that?
Mm-hmm. Yeah.
Okay. Then, well, let's see. So these guys, we can combine together using the quotient rule. For the quotient rule for logarithms. So this would be, these two guys would be the natural log of b plus 1 over b. Does that look okay to you?
Yeah.
Okay. And then what do we have? We have minus 1 over b. And then we have, what, plus 1 minus natural log of 2? And so can we find the limit of that?
Yes.
I think we can, because let's take the natural log of b plus 1 divided by b. You can bring the limit on the interior of the natural log and just take the limit of b plus 1 over b. So if you take that interior limit, that's just going to be 1. So a little explanation on that. Over here, the limit as b goes to infinity, natural log of b plus 1 over b. If the natural log is continuous, we know we can bring the limit on the inside. Whoops. So this is the natural log of the limit. B plus 1 over b. And we know that when the degrees are the same and it's a rational function, the limit's just going to be the ratio of the lead coefficients. So that's the same as the natural log of just 1. So that's where this comes from. And then what's the limit as b goes to infinity of 1 over b?
0.
Minus 0, and then plus 1 minus natural log of 2. So when the dust settles, this guy is going to go to 0, and we're just going to have 1 minus the natural log of 2. Let me scroll down. Do that. Does that seem reasonable to you?
Yeah.
Okay, so really what we want to get out of all this is that the integral converges. So the integral converges. I don't even really care what it converges to. Just the conclusion of the integral theorem, or the integral test rather, says that, oh, if the integral converges, the related series converges. So the series converges. What was there? A series? That guy, way up here. N equals 1 to infinity of 1 divided by what? N squared plus n cubed.
Mm-hmm.
Converges by the integral test, IT. There you go. That's a pretty good one.